More training data is supposed to help. But one deep learning study found a fixed model that performed worse after seeing 4.5 times more samples. The model did not get smaller. The test set did not change. So what moved? Here, worse means worse on unseen examples, the test performance we actually care about, not worse on the examples the model has already memorized. Keep the model and training procedure fixed, and imagine only the training tray getting larger. Every training setup has an effective capacity, not just the parameter count, but what the architecture, optimizer, and training time can fit. As the sample count rises, a threshold moves. Below it, the model is underparameterized and more data usually helps. Near it, the model is just barely able to fit every training example. That barely is the dangerous part. Training error can continue falling to zero, while test error rises. The model has to satisfy a larger set of constraints with barely enough freedom, so the solution that fits every training example can lose the broad structure that worked on unseen data. This is the peak of double descent, a second hill in test error, not the old story that error only rises once and stays there. Keep adding capacity, or move far enough past the critical regime, and the curve can descend again. The Nocturon study reports this non-monotonic behavior in several modern settings and shows a sample-wise case where 4.5 times more samples hurt an intermediate transformer. It is a conditional result, not a ban on data. The paper also did not observe more data harm with optimal early stopping in its tested settings. In a real project, more data is rarely just more independent information. New rows can be mislabeled, duplicated, leaked across a split, or drawn from the wrong distribution. The useful experiment is not count the rows. It is, what information did those rows add, and what exactly did the evaluation measure? First, duplicates. Lee and collaborators found near duplicates throughout common language model datasets, including repeated text in both training and validation. Duplicates can overweight a pattern and make evaluation look easier than genuine generalization. Second, leakage. Kaufman and colleagues define it as target information that should not be available at prediction time. If a future outcome, a user identity, or a near copy crosses the split, the score is answering the wrong question. Third, audit the test labels. Northcutt and collaborators estimated at least 3.3% label errors on average across 10 benchmark datasets, with at least 6% in ImageNet validation. Correcting labels can change which model appears best. Fourth, test the deployment distribution. Recht and collaborators rebuilt Safar, 10, and ImageNet test sets and saw accuracy drops of 3 to 15% and 11 to 14%. And when positives are rare, accuracy can hide the burden. In Saito and Remsmeyer's example, accuracy stayed at 0.6 while precision fell from 0.6 to 0.33 on the imbalanced data. So the rule is not more data makes models worse. The rule is sample count, effective capacity, label quality, split design, and deployment matched metrics are one coupled experiment. Before celebrating a bigger dataset, log the model and optimizer, check for duplicates and leakage, re-audit labels, and evaluate on data that looks like the world you will serve. More rows help when they add independent, correctly labeled information, and when the model and test actually let you use it.